Good morning students, welcome to this session, and here in this session we are learning about the tree and properties of the trees and spanning tree, how to evaluate spanning tree by using different algorithms. These are all we are learning in this session. And in this coming to this, what is a tree? Tree is a connected graph with no cycles. That means there is no loops existing in this graph, and it is a connected graph. What is the meaning of connected graph? If you are taking any two vertices in the graph, that those two vertices having a path, then that graph is said to be a connected graph. That one will be applicable for any pair of vertices in this graph, then the graph is said to be a connected graph. A connected graph with no cycles. Cycles means there is no cycle means v1 to e1 to v2, so like this. So see this, v1 to v2, v2 to v3, v3 to v5, there is a cycle. So such type of cycles are not existing in that graph, then that graph is said to be a tree. So what is a tree? A tree is a connected graph with no cycles is said to be a tree. And here one more point is, any graph without cycles is also called as a forest. Any graph without cycles is also called as a forest. Coming to the examples of the trees, see this, here it is a tree with having only one vertex, and this one having two vertices and one edge. Coming to this one, three vertices having two edges. Coming to this one, see this, 1 2 3 4 5 6 vertices here I have, and here how many edges? 1 2 3 4 5 6. So see this, v1, v2, v3, v4, v5, v6. So here this one is also having 6 vertices and 6 edges. So coming to this one, v1, v2, v3, v4, v5. So v1, v2, v2, v3, v3, v4, v4, v5. So in these are all what are the trees and what are the not trees. Coming to here, there is only one vertex and there is no cycles and it is a connected, so it is a tree. Coming to this one, two vertices, so there is a path between these two vertices, so and it is a connected graph, no cycle, so it is also a tree. Coming to this one, here I have three vertices. Here there is a path between any pair of vertices. v2 to v3 means v2 to v1, v1 to v3, v1 to v2 there is a path, v1 to v3 there is a path, v3 to v2 also there is a path, v3 to v1 and v1 to v2. So such type of path existed here, so it is also a tree. So two vertices tree and it is three vertices tree. Coming to this one, here if you are observing this one, here you see this v1, v2, v3, v4, v5, v6. First of all, check it. Is it connected graph or not? Check it. Connected means there is a path between any pair of vertices. So see this, I am taking v1, v5. There is a path v1 to v3. Sorry, here I forgot one more vertex. So see this, here take this one as v7. So see this, here I want path between v1 to v5. v1 to v5 means here I will come v1 to v7, v7 to v3, v3 to v5. There is a path. No, I want v1, v2 path. So v1 to v7, v7 to v2. So I want v1 to v4, v1 to v7, v7 to v3, v3 to v4. So such type of paths are existing here. So here this is a connected graph and this graph does not having loops, so that does not having cycles. Cycle means wherever you are starting at the same place you have to end, then that is said to be a cycle. So if I started at v1, I will not end v2 yet v1. So if I started at v7, I will not end at v7. So such type of cycles are not existing in this tree, so it is also a tree. This graph is also a tree. Coming to this one, so this here I have a first of all, is it connected graph or not? Check it. So clearly it is a connected graph. There is a path between any pair of vertices. For example, v1, v3, v1 to v5, v5 to v3. I want v3, v4 connected, v3, v5 connected, v3, v2 connected, v3, v1 connected. So everyone is a connected one. Every pair having a root. So it is a connected graph. But here there is a cycle to the there is a cycle in this graph. See this. If I started at V1, V1 to V2, V2 to V3, V3 to V5, V5 to V1, there is a path existed which is a cycle path. So it is not a tree. So it is an example for not a tree. So these are all trees. So this is a tree which having one vertex, this is having two vertices, this is having three vertices, this is having seven vertices. If you are observing, these are all, here there is a common point is existing. Here how many vertices? One vertex, edges, zero edges. Coming to here, two vertices, edges, one edge. Coming to here, three vertices having two edges. Coming to here, what is a 7 vertex having how many edges? 1, 2, 3, 4, 5, 6 edges. So based on the number of vertices, number of edges. So if this one having n vertices, how many edges are existing? N minus 1 edges. So if any graph is a tree, in that should be there is n vertices and n minus 1 edges. So you have to remember that point very clearly. So a graph is said to be a tree. A graph is said to be a tree if the graph is a connected graph with no cycles. That is called a tree. And a tree, one more important point is, if tree having n vertices, that one having n minus 1 edges. So those are all properties of the tree. So what are the properties? There is only one path between every pair of vertices of a tree. So here if you are taking any pair of vertices in a tree, that at that place having only one root existing, there is no other roots are existing. So for example, see this V1 to V4, there is only one path. If you are taking V2 to V4, there is only one path. If you are taking V1 to V2, there is a path, only one path, there is no other path. So such type of paths are existing only one path in the tree. Coming to the second point, if in a graph G there is only one path between every pair of vertices, then also it is said to be a tree. So here it is a property. So based on this property, that one becomes as a tree. A tree with n vertices having n minus n edges. Just now I said that this one having one vertex, 0 edge, two vertex, 1 edge, three vertices, 2 edges, and 7 vertices, 6 edges, n vertices, n minus 1 edges. So that one here I mentioned. Coming to the fourth property, for any positive integer n, if G is a connected graph with n vertices and n minus 1 edges, same property again I am saying here, G is said to be a tree. So connected graph, and here with n vertices and n minus 1 edges, whenever the graph having n vertices and n minus 1 edges, definitely there is no cycle. So in that's why that becomes as a tree. Coming to the equivalent conditions. So what are the equivalent conditions? If one satisfied, obviously other one will be satisfied. So let T be a graph. So here I am taking T is a graph having n vertices. So that graph having n vertices. Then what is the first point? T is a tree. If T is a tree, every two vertices of T are joined by a unique path. It is a tree, it will be satisfied. If it is satisfied, then it is a tree. Coming to third point, T is a connected graph having n minus 1 edges. If these two, any one of these two are satisfying, obviously third one satisfying. So if you are saying T is a tree, obviously it becomes T is a connected graph having n minus 1 edges. If T is a connected graph and having n minus 1 edges, obviously it becomes as a tree. That one is called equivalent condition. Coming to another point, T has no cycles and has n minus 1 edges. So the T graph having no cycles and having n minus 1 edges, then also it is said to be a tree. These four are called equivalent conditions. Any one we are saying that, if we are saying T is a tree, T has no cycles and has n minus 1 edges. If T is a connected graph and has n minus 1 edges, then it becomes as a tree. If T is a tree, every two vertices of T are joined by a unique path. Like this we are saying these are called equivalent conditions. Isomorphism of trees. Let T1 having V1 vertex set E1 edge set and T2 having vertex set V2 edge set E2 are said to be two trees, then these two trees are said to be isomorphic trees if and only if there existing a one-to-one correspondence F from vertex set V1 to vertex set V2 such that if U comma V are adjacent in T1 if and only if their images are adjacent in T2, then those two trees are said to be isomorphic trees. So again I am repeating, isomorphic tree means T1 and T2 are any two trees, then T1, T2 are said to be isomorphic if there exists a one-to-one correspondence F from V1 to V2 such that U comma V are adjacent in T1 if and only if their images are adjacent in T2. So such type of mapping existed, then those two trees are said to be isomorphic trees. Here I given an example. So see this. Here this one having, what is the vertex set of this one? Say this, what are the vertices? V1, V2, V3, V4, V5. And here W1, W2, W3, W4, W5. So here our aim is what? Our aim is to define a mapping between these two vertices. So here I am defining a mapping F from this vertex set to this vertex set such that, how I am defining? Say this, such that I am defining as F of V1 is equal W1, F of V2 is equal W2, F of V3 is equal W3, F of V4 is equal W4, F of V5 is equal W5. If you are observing this, see clearly, V1 having degree 1 and coming to this one, W1 having degree 1. So I mapped with this element. V2 having degree 1, W2 having degree 1. So I mapped these two. V3 having degree 1, W3 also having degree 1. So I mapped these two. V4 having degree 4, W4 having degree 4. So I mapped with V4, W4. V5 having degree 1. So I mapped that one with W4, 5. So like this, I defined this mapping. And clearly, if you are observing this, if you are taking any pair of vertices in the first graph and let it be T1 graph and it is a T2 graph. Now, if you are observing any two vertices, so see this, V1, V4 are adjacent or not? See this, V1, V4 adjacent. What are their images? V1 image W1, V4 image W4. So W1, W4. See this, W1, W4 are adjacent. And V4, V5 are adjacent. See this, what are the images? W4, W5. See this, W4, W5 are adjacent. So like this I defined this mapping. So clearly this mapping satisfying the condition, therefore T1 is isomorphic to T2. This one is one way. And coming to the another one, by using adjacency matrices, so corresponding to the graphs, adjacent matrix of T1 and adjacent matrix of T2, these two we are evaluating. If these two are similar, then also be our graphs are isomorphic graphs. So say this, adjacent matrices means number of vertices. What are the number of vertices? 5 vertices. So adjacent matrix requiring 5 by 5 matrix, V3, V4, V5. Now check it. V1, V4 are adjacent. V1, V4, 1. V4, V1, 1. Next, because of that it is an undirected graph. Next, V2, V4 are adjacent. V2, V4, V4, V2. Yes. Next, V3, V4. So V3, V4 are adjacent. V4, V3. Next, V4 is adjacent to V5. V4 is adjacent to V5. V5 is adjacent to V4. So remaining all becomes how many? 1, 2, 3, 4. So see this? Yes. Remaining all becomes as zeros. So because of that, there is no edge between these all. So this is the adjacent matrix corresponding to the T1. Now similarly, adjacent matrix corresponding to T2. What are T2? W1, W2, W3, W4, W5. Similarly, W1, W2, W3, W4, W5. Coming to the first one. So W1 is adjacent to W4, W1 to W4, W4 to W1, W2 to W4, W2 to W4, W4 to W2, W3 to W4, W3 to W4, W4 to W3. Next, W5, W4, W5 to W4, W4 to W5. Remaining all zeros. Because of that, there is no edge between those vertices. So if you are observing those two adjacent matrices, adjacent matrix of T1, adjacent matrix of T1 graph is similar, is equal to adjacent matrix of T2. That means two graphs are isomorphic. So two graphs are said to be isomorphic means there is a 1-to-1 mapping existing. So what is the meaning of 1-to-1 mapping? If u comma v are adjacent in first graph, their images are adjacent in the second graph. Such type of function is existing, and similarly we are saying that the adjacent matrices of two vertices are also same. So based on these two conditions, these two graphs T1 and T2 are said to be isomorphic graphs. Now see this, every non-trivial tree has at least two vertices of degree 1. That one we have to prove that. What is the meaning of non-trivial? Trivial means that one having only one vertex, then that one is said to be trivial tree. Non-trivial tree means that one having more than two vertices. So two or more than two. Solution, proof, given it's not given, let assume that let capital T be a non-trivial tree. That is T having n vertices and n minus 1 edges, and provided that n greater than or equal to 2. Here we have to mention that at least two vertices of degree 1. Possible, let m vertices having degree 1. So we have n vertices. In those vertices, m vertices having degree 1. What are the remaining vertices? And n minus m vertices having degree more than 1. So this n vertices. So what are the n vertices? Let v1, v2, v3 and so on. vm plus 1, vm plus 2 plus and so on. These are the vertices. So here I said that these are all having degree 1. What about these are all vertices having degree greater than or equal to 2? So this is our concept. So we know that sum of the degree is equal to 2 times of number of edges, which is equal to 2 into what are the number of edges? N minus 1, which is equal to 2n minus 2. This is the one of the point. Coming to the another one, sum of the degree. Now I am calculating sum of the degree. How many vertices having degree 1? M vertices. So 1 into m plus remaining vertices. What are the remaining vertices? N minus m. So n minus m having vertex degree greater than or equal to 2. So this one greater than or equal to 2 into n minus m. That implies sum of the degree is what is the value? 2n minus 2 greater than or equal to m plus 2n minus 2m. 2n getting cancelled. What is remaining? Minus 2 greater than or equal to minus m. What is this? Multiply minus inside. So 2 less than or equal to m, which is nothing but m greater than or equal to 2. M greater than or equal to 2 means what is m? M vertices having degree 1. That means minimum 2 vertices having degree 1. That means this is the definition, at least 2 vertices having degree 1. Therefore, every non-trivial tree having at least 2 vertices of degree 1. So this is the problem. So what I done here, again I am saying this, let T be a non-trivial tree, T having n vertices and n minus 1 edges. Particularly he given non-trivial, that means n is always greater than or equal to 2. I assumed that m vertices having degree 1. Now m vertices are completed, so m vertices completed, remaining are n minus m. So n minus 1 m vertices having degree more than 1. So we know that sum of the degree is equal to 2 times of number of edges. So 2 into number of edges edges of the tree are n minus 1, which is equal to 2n minus 2. So what is the definition? Sum of the degree is equal, actually what is the sum of the degree? This total degree m, and this one becomes as a greater than or equal to 2. In that way, greater than or equal to 2 into n minus m vertices. So already we evaluated sum of the degree is equal to 2n minus 2. Apply and simplify this one, you will get m greater than or equal to 2. Therefore, not here. Therefore, non-trivial T having at least 2 vertices of degree 1. Therefore, every non-trivial tree has at least 2 vertices of degree 1. 2 vertices of degree 1. So this is the proof of the given statement. Now we are going through a problem. So what is that problem? A tree has 2 vertices of degree 2, 1 vertex of degree 3, 1 vertex of degree 3, and 3 vertices of degree 4, and 3 vertices of degree 3, 3 vertices of degree 4. Then find how many vertices of degree 1. How many vertices of degree 1 does it have? So here we have to calculate this one. Here, first of all, how many vertices this one having? Check it. So solution, See this tree has two vertices, so these are the vertices and this is the degree. How many vertices? Two vertices having degree 2, one vertex having degree 3 and 3 vertices having degree 4. And how many vertices of degree 1 does it have? So first assume that this tree having n vertices. This tree having n vertices. So how many completed? 3, 4, 2, 6. 6 vertices completed. What are the remaining? N minus 6. So how many vertices of degree 1 does it have? So these vertices having degree 1 we have to calculate. So here I want to calculate number of vertices having degree 1. So let the number of vertices are x having degree 1. So these are the vertices. So how many vertices? X plus 6 vertices we have. So those vertices having, so total number of vertices x plus 6. X plus 6 number of vertices, so this is equal to n. So this graph having how many edges? X plus 6 minus 1, that means x plus 5. So x plus 5 edges this graph consisting. Now we know the formula. What is the formula? Sum of the degree is equal to 2 times of number of edges. Sum of the degree means these are all. So 2 times. So 2 into 2 plus 3 into 1 plus 4 into 3 plus 1 into x is equal to 2 times of number of edges. How many edges this one? Having x plus 5. So which is equal to x plus 5. That implies 4 plus 3 plus 12 plus x is equal to x plus 10, which implies 12, 16, 19 plus x is equal to x plus 10. That implies this 10 comes to this side, that x goes to that side. 19 minus 10 is equal to x minus x. That means x is equal 9. So x is equal to 9 means number of vertices of degree 1 are 9. So this tree having 9 vertices of degree 1. So like this we are completing the problem. So we are going through the next topic.